and welcome back to another video with ItsDrDan, and today we're going to be learning about the strength of acids and bases. And the whole idea here is that acids and bases, they dissociate when dissolved when they're added to aqueous solutions. Now, whenever you have acids and bases, the reason they dissolve is that they are considered to be electrolytes. Now, the thing with electrolytes is that there's two major definitions. There are strong electrolytes, and there's also weak. Now, strong electrolytes, the most important thing about them is that when they dissociate completely, meaning that what we mean when we say that is that when you throw, let's say, HA into solution, it's going to be making all hydrogen ions and A minus ions when that's thrown into solution. So all ions when we are here, right? There's going to be no more remnants of the major molecule when that's thrown in. And the same thing applies to bases too, right? If you throw a strong base, let's say like sodium hydroxide, you will get B plus and then all OH minuses in solution. They completely dissociate. Now with weak, they partially dissociate. They're still considered acids and bases. They still conduct electricity. However, it's a lot less because you don't have as many positive and negative cations and anions in solution. There's a lot less. So when it comes to the solution, so up above, I use a giant arrow to show complete dissociation. Up here, even though we still will write that it makes H plus and A minus as it dissociates, there's not going to be as many in solution. So you'll notice is that there's a bunch of HA molecules that are still connected together. Notice how there's no charge on them. They're just in their molecular form. And then you'll have a few ions in solution. So you still write the same dissociation, but there's not going to be as many in terms of the concentration of ions in solution. Now, with this, we essentially, as chemists, we use what we refer to as an equilibrium constant, which is called the acid dissociation constant to tell you how strong or how weak it is. This is the same thing as a K value, but instead, the only difference is that we put a little a next to it to tell you, hey, we're referring to acids. So there's an acid dissociation constant, and then there's also a base dissociation constant, which is a KB. We typically only really use Ka though, 99% of the time. So when it comes to Kas, the whole idea here is that they determine the strength of the acid. So the bigger the value there is, the more products. The smaller the value there is, the more reactants. So the more H plus ions that are made, the more electricity that you'll have, the stronger it's going to be. So using this whole products over reactants idea. So drill that saying in your head, products over reactants, because when it comes to equilibrium, we're going to be saying that quite frequently when we're trying to write these different equations. So when it comes to them being strong, whether it's a strong acid or a strong electrolyte, typically that Ka is much greater than 1 because there are a ton of ions, right? All products in there. So this number is really, really big. And as a result, this number is as tiny as it can get because you have all products, meaning it's kind of like saying, what is 10,000 ions compared to one molecule, right? So it's like a 10,000 to 1. That's huge, right? As a difference. Whereas when you have like a weak acid, well, it's going to be like the opposite. It's kind of like saying, hey, we have one ion in solution and 10,000 molecules there. So what's 1 divided by 10,000? It's going to be a really small decimal value. It's all about the ratios of how we are looking at these. Let's go look at some different examples of this. So when we are writing these, the first thing we got to do is understand and be able to write reversible arrows because they allow us to be able to represent weak acids and bases. So let's say if I have an acid and a base here, so I have HA, which is our acid, and water in this case is going to be a base. So that means that HA is going to donate its proton to water. So we'll write that out. And as a result, we're going to have A minus and then H3O plus or hydronium. Now, when we are writing this, there's a couple notes that need to be made, is we're going to write our Ka equation. When we are writing them, we never include solids or pure liquids like water. The reason we don't include them is that their concentration is considered to be constant. In terms of water, there's so much water in solution that your values won't make any sense because they don't represent the actual chemistry that's occurring. We only are curious about the solute or the very tiny piece of it. So if we were to write this Ka equation, the next thing that we got to do is do products over reactants. But how do we show them? Well, we use brackets to indicate molarity when we are writing these. So every product and every reactant is going to be surrounded by square brackets, which will indicate how much molarity there is. So let's do that. So if we have, let's say, A minus, so we'll put that in brackets. So products, A minus, and H3O plus. So from our formula on the top, and that's all going to be divided by the reactants. So products over reactants. We don't include water, so we're just going to write A minus, H3O plus, all over HA in brackets. Now, the reason we only include these other ones is because they are all aqueous, right? So every one of these is aqueous, and then water is considered to be a liquid, so we don't write that one. So now the thing about this, if you calculate this, so if we had all the concentrations, we had them all measured, you usually would get a Ka that's very small. You might get one that's 10 to the negative 1 to 10 to the negative 14. It's usually very, very small when you're talking about weak acids and using Ka values. Now, the thing about these, though, the strength and molarity of an acid determine the acid's Ka. Okay, so depending on how strong of an acid it is and what the concentration. Now, the thing to keep in mind, an acid can be considered strong, meaning HCl, sulfuric acid, nitric acid, but it can have a diluted concentration. So don't just think like, oh, when we say something is strong, it means that it's like very powerful. It could be, a very little molarity. And the other thing about it is that you can also have a weak acid that has a very, very high molarity. So they're not relevant to each other, molarity and the strength is what I'm trying to say. Let's look at some examples of this. All right, so our first one here, looking at acid-base equilibrium. The first thing is we got to write out our reaction. So we have HCl reacting with water. HCl is a strong acid, so it's going to be donating its proton to water. And as a result, what are we going to be making? Well, we will have Cl minus as one product, and then the other one is going to be H3O plus that we're going to make as well. Now, when we are trying to write out the Ka factor, being that I gave a value for Ka, so with this one, it's a strong acid. So notice that it's a very big number, 1.3 times 10 to the 6th power, right? That's telling you have 6 zeros behind this. So it's over 1 million is how big this is. It's very large. So what we will do is we'd write 1.3 times 10 to the 6th and equal that to products over reactants. So what we'll do is we'll use square brackets. We have chlorine ion, then H3O plus ion, and then all that's going to be over HCl, and we exclude water because water is considered the solvent and is a pure substance. So that's how you would write that. Now, the other thing here we have down below is HF and water. Now, the one thing to kind of point out about these two different reactions is notice the arrows and their difference here, right? The HCl plus water has a single arrow. Hydrofluoric acid, or HF, has a reversible arrow. So we use reversible to denote whenever it's weak in a weak acid or base. And we use a single arrow to say, hey, we have a strong acid or base. So it's one way to be able to see the difference when you see it. So with this one, HF is the acid, so it donates its proton. So what we're going to have is F minus left over, and then H3O plus as your other ion. So if we were to write out the Ka, so we'd have Ka is equal to F minus in brackets times H3O plus in brackets all over the concentration of HF. And that's how you'd write out an equilibrium constant. And the thing that's important here is it tells you that being that this is a lot less than 1 is that it favors the reactants. So most of the population of this solution is going to be on the left-hand side. Whereas when we were looking at the right one, that one was greater than 1. So most of that is going to be on the right-hand side of the equation. Let's go look at some more. Di and tri-protic acids also exist. Now, these are generally weak acids that have multiple hydrogens. So one example is carbonic acid, which is a diprotic acid, meaning 2 protons, diprotic. So if you have those 2 hydrogens, they will dissociate. However, when it comes to acids, you don't rip them all off at once. They lose one at a time, right? So acids lose 1 proton at a time. That is very important to realize, is 1 at a time. So here I have H2CO3 yields H plus and HCO3 minus when you throw it into water. So how would we write this in terms of the Ka value? So being that it has multiple protons, you'll kind of notice on the right hand or the left hand side here is that there's a Ka1. So it's telling you the first proton comes off. So the way that we would say this is we have Ka1 and we put H plus in brackets, HCO3 minus in brackets, and then the H2CO3 on the bottom. So this would be the first one. Now, being that this has multiple protons, the thing about it is that, well, the reaction could keep going, actually. You can actually write more. So we can actually take, let's say if we had a second Ka value, we can bring that up here. And we can actually say, oh, well, what would happen if I took, let's say, HCO3 minus, and I wanted to further dissociate this? How would this actually work? Well, it would make essentially H plus, and then CO minus would be the other ingredient as this dissociated even further. And then we could write a KO, essentially another Ka value for the next portion. And notice that the charges change too, right? We have a minus and then a 2 minus on the next part, right? It slowly loses more and more. And we have a different Ka value for the next part. Notice how the value is a lot smaller, telling you that this isn't as common. There's very little of these products actually existing in solution. So carbonic acid, the neat part about it is this is actually the chemical that helps maintain the pH of your blood. So this is what establishes itself to make sure that your pH does not change by very much when you essentially eat anything or drink anything, or anything like that gets in contact with your body that has no harmful effects. Let's take a look at some more examples. The autoionization of water means that water can automatically ionize itself when it's in a solution of itself. So water can act as either an acid or a base, which is one of the most unique characteristics of it. It allows it to do all kinds of chemistry as a result. Now, being that it can be either, so anytime you have a substance that can do both, this is referred to as amphoteric, meaning it can do either an acid or a base. So if I have, let's say, 2 water molecules and they want to react with each other, which one's the acid, which one's the base? Well, we can choose, right? It doesn't have to necessarily be one or the other. So let's say the one on the left is the acid, and then the one on the right is the base. So what exactly are you going to make as a result? Well, if we donate our proton to the other one, we are going to pretty much have on the left-hand side, what's left is OH minus, and then we'll also have H plus as a result, which if you kind of remember, that is your Arrhenius acid base definition. Water produces protons and it produces hydroxides. It also follows the Bronsted-Lowry definition, right? It donated a proton, it received a proton, it fits both. So they can do that. So whenever we are looking at some of these different chemicals, right, can we see that, well, when we have a water, can we have where one water molecule donates its proton to the other side and gives away its proton as a result. All right, so with that being donated, we have essentially a really, really happy water who has an extra positivity behind it, and then a very sad water who lost its poor little proton. So whenever we have an H plus release by an acid, water will pick it up, okay? So one thing about this that's really important to realize is that H plus is generally written to talk about how acidic something is. We can also use hydronium ion to represent that too. So H3O plus. So those two are generally considered to be equivalent to one another in solution. So there's two different ways to look at this, right? Acids can dissociate to make H plus, or we can also say that acids increase how much H3O plus there are in solution. Both tell you that the pH of these different solutions is going to essentially be going lower and lower and lower, or more acidic as a result, because of this increase in hydrogen concentration. So they both are equivalent to each other, which is really important to write down and note. All right, let's take a look at the next part. Other examples are of polyprotic ions. Other examples of amphoteric molecules are polyprotic ions. So something like HCO3- can behave like both an acid and a base. So meaning that it either can donate a hydrogen or receive one. So for example, if I were to draw on both sides the different types of how can this molecule go, if I have an additional proton, we will have carbonic acid, right? So H2CO3. And on the other way, if I lose a proton, I will have CO3 2-. So with this particular molecule, it could either receive one or it could donate one away. So when it comes to acid bases, it depends on how you look at it, right? If it went this way, essentially it is receiving one, so it's actually acting like a base. If it goes the other way to the right, it's acting like an acid. So it's all about what direction do we actually see it going when it comes to being an acid or a base, or accepting or donating. Let's look at the next part. Now, the most important part, what comes with the autoionization of water, is all about that relationship. It is a bronsted-lowry and or acid and base. It's also an Arrhenius acid and base. So when it comes to writing the K factor for this, one thing we can actually do for this is we can write that K factor as essentially H plus times OH minus, and we exclude the waters. Now, why is that so important? Is it tells you you have an inverse relationship, meaning that as H plus goes up, OH minus goes down, and the opposites occur as well, right? As the acidity goes down, the more alkaline or basic it is goes up. So one thing that we can actually do here is that there is a relationship here at room temperature for this constant. So we call it a Kw constant. So it's all about water dissociation. And what we have here is H plus times OH minus. So that those two concentrations multiplied by each other equals 1.0 times 10 to the negative 14. So now why is that so big is that no matter what concentration in solution you have of H plus or hydrogen ion or protons and hydroxide ions, if you multiply those two concentrations together, you're always going to get 1.0 times 10 to the negative 14. So this is a really very important formula to realize of what the scale is of acidity when it comes to room temperature solutions. And one thing you might realize is that, okay, I have that 14 number all the way at the top. Well, one thing to think about is what's the size of the pH scale? And you might remember, or you're going to learn about, is that the pH scale goes from generally about 0 to 14. So what this number is going to lead to is what your pH scale is, which is an easier way to be able to see how acidic or basic something is, rather than looking at molarities and concentrations all the time. Let's keep moving. So the next part, realizing that's to do with solutions. Let's talk about neutrality. Well, if you have a neutral solution, this is referred to as a pH of 7, right? So it's right in the middle of your pH scale. how did they get that value? Where does it come from? So let's say if I had the following value, where if you have a neutral solution, that means the acidity is equal to how basic or alkaline the solution is. So meaning H plus is equal to hydroxide. So if they're equal, let's do some simple math to kind of think about that. How does that work? Well, if they're the same, let's just use a variable to describe that. So let's say that I have H plus here and OH minus, and let's just say that they're equal to, let's just say X, being that we're used to algebra, we've used X probably most of your lives. So if we say, hey, we have X times X, and that's equal to 1.0 times 10 to the negative 14. What's the first thing you can do? Let's do X times X. What do you get? Well, you'd have X squared. So now if I have X squared and I have 1.0 times 10 to the negative 14, how do you get X by itself? How do you cancel out the square? Well, the thing you can do is we can square root it, right? We can square root both sides. So if that's to happen, right, these cancel out. And what you are going to get is that X is equal to 1.0 times 10 to the negative 7. Now, why is that so important? Is if you think of neutrality, so with the 7 value, one of the most important factors is that if you have a pH equal to 7, that's considered to be neutral. So let's try to see of what implications this means in terms of determining if something's acidic or basic. When we have something that's considered to be neutral, that is when the hydrogen concentration, or the protons, are equal to the hydroxide concentration, or OH minus. So when these are equal, the concentration of each of them is going to be 10 to the negative 7th power, and that's going to be molarity. So that's a pH of 7. Now, when something is acidic, that means you have way more protons in solution. So we're going to increase that number and also decrease hydroxide. Remember, there's a relationship. As one goes up, the other goes down. So that means that you're going to have a bigger number for 10 to the minus 7, like 10 to the minus 5, 4, 3, 2. So it's getting larger, that number, right? It's going to be like 0.001, 0.01, much bigger. When it's basic, that means that number is going to be a lot smaller. So anywhere from like 10 to the negative 8 to 10 to the negative 14, for example. So if we were to try to do this as an example, and I asked you, what kind of solution do we have if you have 1.0 times 10 to the negative 4 as your concentration? Is that bigger or smaller? Now, for a lot of students, it's usually really hard to try to understand and interpret scientific notation. So for this one, if you were to really think about it, well, how many times am I really moving that decimal place? Well, that's going to be 0.001. Now, is that bigger or greater than neutral? Well, neutral is negative 7. So we have 1, 2, 3, 4, 5, 6, 7. Which one is larger? And you can see really quickly that the one on the left, which is our original number, is a lot bigger than the other one, right? It's sometimes that power is misleading when you see that. So what that tells you is that this is very acidic. Now, if I ask you a follow-up question, how do you figure out what the hydroxide concentration is? Well, if you had to do that, we could rearrange that equation up there. And we could essentially say that, all right, well, I have OH minus. I'll divide the H plus from the other side. So 1.0 times 10 to the negative 14. Divide that by the H plus concentration, and we could figure out what the OH minus is. So let's plug in our number. What would we get? So as a result, we would have 1.0 times 10 to the negative 14 divided by 1.0 times 10 to the negative 4, and you'd quickly find out that that is going to be about 1.0 times 10 to the negative 10 molarity when it comes to the concentration of OH minus. So notice that it's a lot smaller of a value. It's 10 to the negative 10 power. So it should be an inverse relationship. And this is how you can try to solve this particular problem. So let's go to our final summary. When it comes to trying to understand the strengths of acids and bases, it fully depends on the level of chemistry you're taking. If you're taking just introductory chemistry, which is just for beginners in chemistry, I would recommend really memorizing your strong acids and bases. It's a very good starting point to go. Same thing if you're in general chemistry 1 as well. There are 7 strong acids And then we also have the strong bases, which is all of the soluble hydroxide salts, which are mainly the alkali metals. So all the alkali metals, and then essentially the first 3 alkaline metals on your periodic table. So if you remember those, you generally will be fine knowing the majority of chemicals. If you don't see one of these, that means it's weak. About 98% of acids and bases or more are weak acids and bases. But if you know these 7, it will save you a lot of time and frustration. So strength is all about looking at the equilibrium values, which we'll look in more detail in future videos. But this is an idea of the basic idea of how to set this up and understand where the pH scale comes from. Is all about how strong an acid or base is. And that's what we'll look into in our next video. So thank you so much for listening. I hope that this video helped you. If you're confused, reach out to me and ask for help. If you're not one of my students and you still want to help and learn more, comment below and let me know what you thought. And if this is your first time here, please hit that like and subscribe button and let me know if you ever need anything at all for your chemistry needs. If you want a particular video, let me know and I'll see if I can help you and try to make future content for you. All right, thank you so much, and I hope you have a wonderful day, and I'll see you all later. Bye now.